On to Chapter 2, Physics in Action. This chapter is about the physics of sports. There's our essential questions. Remember that in this recording you can pause, rewind, speed up, slow down, whatever you need to do to make sure that you get the information and update your notes as you need. So we had our what do you think questions, multiple this time. Hopefully you've got that filled out. In the investigate, we rolled an object down a curved ramp. In this case, we had a skateboard, and observed its motion. Then we changed the slope of the track and predicted how high the ball would go. We introduced the concept of inertia through experimental results. We learned that without friction, the objects were able to skate to the same height, but with friction, the objects were not able to skate to the same height, as shown here in the little video. Sorry, kitty. Galileo Galilei. He is responsible for the law of inertia. Inertia is the resistance to start or stop moving with a constant velocity. More mass means more inertia, and more inertia means you have more resistance to start or stop moving with a constant velocity. Inertia is determined by mass only, not by size, shape, volume, or velocity. Before Galileo's work, people thought objects would always stop moving eventually. Galileo's thought experiment was a ball on a hard curved surface, like we observed, would continue to reach the same height forever. A thought experiment is just an imaginary experiment in his head. After Galileo's work, people thought objects would move forever unless a force was exerted on them. Isaac Newton came up with his first law of motion. First, before we get into that, it's important to know what a net force is. A net force, or sigma F, is the total force acting on an object. Newton's first law says that when the net force equals 0 on an object, that object will have a constant velocity, which can also be 0. Looking at these two images, we have in the lower left corner the rightward purple force to the acting on the book, which equals 20 newtons. Newton is the unit of measurement for a force. And the yellow force acting in the negative direction, or the left direction, also equaling 20 newtons. So our net force here is 0. When we add up all of the forces, add the positives and negatives, we get 0 newtons. That means that book is having a constant velocity. Picture on the right, we have two people connected to something, I don't know, a refrigerator. The person on the left is exerting 10 newtons to the left, and the person on the right is exerting 5 newtons of force to the right. So the net force is 5 newtons to the left, or negative 5 newtons. In the first image, the book, constant velocity. In the second image, the refrigerator, not a constant velocity. That means we are accelerating because of Newton's second law of motion, which we're going to get into later on in the chapter. Here's an example. Which has more inertia? Pause the video, read the options, and then come back and I'll give you the answer. The object with more inertia is the object that has more mass. So we have a 100-kilogram football player. We don't care about how fast they're running. We don't care if it's all muscle or all fat. It's just more inertia. It's going to be a lot harder to move a 100-kilogram person, which is about 220 pounds, than it is to move a 10-kilogram football player, which is about 20 pounds. That's a tiny football player. Some sports require running starts. They don't really require it, it's just the athletes use running starts to gain an advantage. Velocity is how fast an object is moving, including the direction, from previous sections. In the video, you see a javelin thrower throwing their javelin. To make sure the javelin goes furthest, The thrower wants to make sure the javelin has the highest horizontal speed as possible. So to assist them, the throwers will get a running start. This way, the velocity of the javelin becomes the velocity of the thrower's hand as they release, the velocity of the elbow, the velocity of the shoulder, and the velocity of the body all together, because velocity is a vector, directions matter, it's all moving in the forward direction, so the javelin is going to get a higher speed. For example, if we have 3 meters per second for the hand, 2 meters per second for the elbow, 1 meter per second for the shoulder, and 4 meters per second for the body, the javelin's velocity, once released, will be 10 meters per second. We're not going to do any calculations with this particular equation, but it's useful for you to know and understand how we can add things together. Next, I want to talk about frames of reference. Objects are moving relative to some surface. Objects moving relative to some surface may appear to be moving faster or slower depending on who is looking. Objects in the opposite direction would have a negative velocity. This is the sensation that you get when you're moving down the road and you see cars traveling in the same direction as you. If they're moving faster than you, you see them go ahead. If you are moving faster than somebody else, that car appears to you to be going backwards in the opposite direction. If the car is moving in the opposite direction as you, then those cars are going to appear faster than they're actually moving. We have an equation to help explain this, where we have our apparent velocity, which is the velocity of the thing we care about. Then the object's velocity is going to be the velocity of the object we care about, so the true velocity. And then we have the frame of reference velocity, which is the velocity of the moving frame of reference. For the example of us in the car, if we were moving forward at 10 meters per second, then we look over to the right and we have a car moving at 30 meters per second. The apparent velocity of that car is going to be 30 meters per second, the true velocity, minus our velocity, which will be negative 10 meters per second. We'll get to more examples. But if you watch this example, let me move my head out of the way, we can see the different speeds from the perspective of the bird or the squirrel or the car as they're moving. So the car moves forward. Things that are going in the opposite direction are going to have a negative velocity relative to the car. And the things that are moving slower will also have a negative velocity relative to the car. To the squirrel who's just standing on the side of the road, they're able to see the actual true speeds because their frame of reference speed is 0. So we're subtracting 0. When you're in a car, to you, everything in that car is not moving. If you squat down, you can't see out the window. Everything's going to appear to be stationary. The only way you would know you are moving is by feeling the car accelerate. When you get up and you look around, out the window, now you can see trees passing, so you realize you are moving relative to the ground. You're staring at your phone and you can't see outside, though. That phone doesn't appear to be moving to you. For the javelin, which has that speed of 10 meters per second, from the perspective of the audience, the javelin speed, 10 meters per second, plus the audience's speed, which is 0 because they're not moving, to the audience, that javelin appears to be moving 10 meters per second. For the audience, from the perspective of the javelin, the audience appears to be moving. That's not right there. The audience is not moving. That's their true speed. 0 is their true speed. The javelin is moving in the negative direction. So the audience appears to be moving 10 meters per second opposite of the javelin. We won't do a lot of calculations with this, but it's useful for you to understand again. There will be some calculations, so don't just skip it. Here's an example. Quarterback runs backward at 1.5 meters per second while throwing a ball forward at 10 meters per second. What is the ball's velocity relative to the ground? For this, we're going to use forward as positive. Pause the video, try it for yourself. Here comes the solution. Using our frame of reference, we get the apparent speed of 8.5 meters per second forward. The velocity of the ball is the velocity of the quarterback is 1.5 meters per second backwards, so negative, plus throwing the ball forward at 10 meters per second. So we get an apparent velocity relative to the ground of 8.5 meters per second. So here's some reflection questions for you. Now it's time for you to go practice for yourself.